thank you very much for the invitation. I'm happy for being here, and thank you for you still being here, although we are a little bit late. So today I will talk about training generative neural networks using the Bures-Wasserstein laws. So it's a little bit different architecture than the one it was introduced before by Andrea. So here, what we will try to do is like to use deep linear networks to learn the covariance matrix and using the Bures-Wasserstein laws. And what it is widely used in the literature is like the mean square laws and the squared laws. But Bures-Wasserstein is qualitatively different than the usual squared laws. And but we are using also at the same time, we are using generative neural networks, and we are trying to learn the parameters of these generative methods. So what we will describe here is like we will try to characterize the critical points of Bures-Wasserstein type of laws, and we have a rank constraint problem, and we will show that this the Bures-Wasserstein gradient descent, the Bures-Wasserstein gradient flow achieves an exponential rate of convergence, and at the end we will show also some numerical illustrations for the linear rate of convergence. So first we will describe a little bit the model that we are using. So we have an input. The input is a latent Gaussian distribution, and by this we mean like with a zero mean, and the identity as a covariance matrix. And then what we want to do is like to input this latent Gaussian distribution to a linear neural network. By that we mean that we have like n layers of n layers, and the activation is just the identity. And so the parameters that we want to learn is these matrices, and this is our parameter space, and then we have this function space, which is the end-to-end matrices, because when we enter this linear neural network, we have this matrix factorization here. And okay, and what it is really well known is when we have like matrix factorization through a Gaussian distribution, then the linear neural network will follow also a Gaussian distribution with zero mean and covariance matrix sigma. And this is actually our parameterized covariance sigma. And we will use this parameterized covariance to learn the target. So the target is sigma naught, and it's positive positive definite matrix, and with spectral decomposition with the following. So what we will do is here we introduce the Bures-Wasserstein laws on the space of covariance matrices, and sigma, if you recall, is just the WW transpose, and is a positive semi-definite matrix. And the Bures-Wasserstein laws is just the Wasserstein between the two Wasserstein distance between two zero mean Gaussian distributions. So, but when we try to optimize, what's happening is we have this square root here, and sigma. Usually, what's happening during training is that drops rank, and we have vanishing singular values. So the Bures-Wasserstein loss is not smooth at the matrices with a singular value, and somehow, in order to prove the convergence, we need to somehow to find a remedy for this behavior. So what we are doing is just we perturb our covariance, our parameterized covariance matrix by tau, and tau is like it's not any parameter. It's like it should be also bounded from below by the minimum singular value of the target distribution of the target covariance matrix. Okay, so but now if you remember, we have seen like that we have like the parameter function and the parameter space, which is just the tuples of W's, the different layers, the matrices of the different layers. And then we have also the function space, which is just the end-to-end matrices. So it really depends on the search variable that we are using. So here, like, we will see the results for the perturbative loss, but we can transfer also the results to the original one. But for the sake of simplicity, that we will just discuss the perturbative loss. And the first thing that we will discuss is the critical points of the perturbative loss. So again, we are dealing with a minimization problem where it is the minimization is taken over rank constrained matrices. And by that, what we mean is we have this manifold of end-to-end matrices. N is the output dimension, M is the output dimension, and rank of W is K. And this means just that, like, either will be, it depends, like the structure of the neural network. If the neural network, if the linear neural network has a bottleneck, so then the rank, it will be the minimum of dimension of the layers, or like the input or the output dimension. So basically what we are finding here is like that the critical points on the function space of the perturbative loss satisfy this eigenvalue decomposition, and which basically agrees with the critical points on the function space if we use not the Bures-Wasserstein distance, but the square loss. And then here also we have the same happens for the critical points on the covariance space. Again, they satisfy this eigenvalue decomposition, which is similar to the one if we are using the square loss. And here is like also a question like which arises or like a statement that, okay, we can have a low rank approximation of the target covariance matrix using the Bures-Wasserstein laws, and as a parameterized function, the deep linear neural networks. So basically, how we derive these critical points is just like the gradient of the loss. We take the points where the gradient of the loss is vanishing, and this is the similar result to Eckhart-Mirsky, which is actually shows this low rank approximation for using the square loss, but the square loss is a unitary invariant norm, which this doesn't happen with Wasserstein, with the Bures-Wasserstein. So what we saw actually is that for the perturbative loss, we achieve the highest rank, tau approximation of the target, but we will see later how we can do that. So basically now it comes the convergence part. So basically we need to put assumptions on our neural network. So the first assumption is just like, okay, this formula here is just a variational formulation of the Bures-Wasserstein. And by this, what we want to say, it's just like the target so what we want to say that we have to initialize around the target covariance. And then the second assumption that we want to put is just that the weights are balanced. So this means that during training, our matrices does not drop rank. So which happens usually in with deep linear neural networks and generally with neural networks that during training we are losing, like we are dropping rank. So basically these assumptions ensures that during training we will not have lose rank, but we don't know what will happen in the limit. So in the limit we might lose rank. We don't know that yet, and it's an open problem what's happening in the limit. And then under these assumptions, what we can prove under this balanced weights assumption and modified margin deficiency, then we can prove that then if we are using this as an evolution rule for our parameters, then we can prove that someone can achieve epsilon precision on the loss L tau after p iterations, and the p iteration is exactly this formula. It's a little bit ugly. Eta is the learning rate, n is the parameters of our the number of the layers, and c is this margin deficiency, like how close is how close is the initialization of our weights to the target one. And then basically we can see here this the convergence of the linear convergence of gradient descent, Bures-Wasserstein gradient descent, and here it is as a function of depth. So here we vary the depth, but we fix the minimum singular value. And then finally, under the same context, when we assume like balanced weights and modified efficiency margin, again, and if we define the gradient flow of the parameters using this equation, then actually we can prove that the Bures-Wasserstein gradient flow achieves the exponential rate. Again, it depends linearly from C. And C, again, it has to do with the minimum singular value of the target covariance matrix, and n is the number of layers, and delta naught is the distance from sigma naught to the optimal solution, and k is just like a parameter, like of the strong convexity of our loss function when we use this perturbation. And then finally, we see that with using these hyperabolas, that when we vary the minimum singular value and the depth, we see that still we have this linear dependency for the convergence of the convergence rate. And another thing that we observe is like why it's better to use Bures-Wasserstein instead of using square loss. We see here some stability for the Bures-Wasserstein gradient descent, which is not observable in it's not the same for the square loss. So basically, this graph here shows that the upper bounds on the spectrum of the Hessian, and here I is referring to the index of the critical point. And then what we see that like when we have negative eigenvalues correspond to saddle points, and then these eigenvalues escape, we can prove that the dynamics can escape the decent directions. So if the negative eigenvalues of the Hessian are large in absolute value, then this means that the gradient descent escapes the saddle points, and it's something that we observe here from this graph. And then what this means, which is actually another interesting point to use the Bures-Wasserstein, is that the gradient descent of the Bures-Wasserstein escapes saddle points, but we're not able to show it mathematically yet, but we are optimistic that we can do it. And finally, I want to summarize, like when we have like the regular, the original loss function, and we use the parameterization is these end-to-end matrices, then the critical points are exactly the highest rank, where ZK indicates it's the JK is the index of the cardinality, and its exact K, the highest eigenvalues. And the same for L tau 1, which is the shifted, the perturbative loss, and the parameterization is these end-to-end matrices. It's on the function space. When we say end-to-end matrices, we mean function space. And here, like, it's just like the original ones, but shifted by tau. And again, tau, it's not like any. It has to be bounded by this the sigma mean of the target. And finally, here we have like the results for the convergence. And then here, if we have like balanced weights, and then we use like this margin deficient, this modified deficiency margin, we see for the gradient flow, we have exponential rate, and then for gradient descent, we achieve accuracy log 1 over epsilon. Again, here it's like, I mean, we have managed to find the critical points of every type of loss, like depending on the search variable, but we are not able to connect the critical points with the convergent results. That actually the convergence, actually the gradient descent converges to this to one of the critical points. So okay, I'm almost done. So what we are wishing to do next is like to relax this balanced assumption and this margin deficiency assumption. And by this, like if we understand the evolution of singular values during training, we might be able to do it. And then extend the results for Gaussian processes, because now we used a simple neural network, and we used a simple, we used just Gaussian distribution, so we want to extend it with Gaussian processes. And I think that's what I wanted to say. Thank you very much.